Next up on our list here is we are looking at kinetic energy and work energy and how those apply, and it'll all hopefully make sense before we're done here. All right, first off, energy. Energy is the ability to do work. So if we can do work, then we have energy. Or if we can do work, we can have energy. Work gives us energy, etc. Kinetic energy is the energy of motion. So when we talk about work and kinetic energy coming together, obviously it's moving to do work, which you have to do, right? If you're not moving, you're not doing work based on the definition of work. So they two really fit together really nicely. So for example, we got a car that's applying a constant force, right? And it's going from this velocity to this velocity, so it's going to speed up, because if you apply a force, you should accelerate. The net work done, okay, is going to be based off of the net force times the distance. And we have to, have to do some math to do that, but we can use kinetic energy to find that. If we knew the mass and we knew the velocities, we can find what the kinetic energy is. And so work and kinetic energy fit together. So here's an example. We got a 3,900 kilogram truck moving at 6 meters per second. What is its kinetic energy? So kinetic energy is 1/2 mass times the velocity squared. So as we look at our truck, we know that our mass of our truck is 3,900 kilograms. And our velocity is 6 meters per second. And then we just square that, and we get, and I'm just going to round this, 70,000 joules of kinetic energy. What happens if the speed is doubled? So this is more of a theoretical question. I mean, you could take the speed, put it at 12, and put it in there, and you'll get the same answer I'm going to give you here. But let's think about this for a second. Because the speed is squared, if we double it, all right, if we make the speed twice as much, we're squaring twice as much, or making it 4 times as much energy. So all we do is we take our 70,000 and we multiply by 4, and that equals 280,000 joules. So again, you can do the math yourself, but just understand that we can do a quick calculation this way, and we can see that 280,000 joules will be our kinetic energy if we double our speed. Okay, so how work and energy fit together? And here's the formula. Obviously, the change in kinetic energy is equal to the net work done, as we showed as we showed here, right? The change in kinetic energy is equal to the work done, net work done. So kinetic energy, the equation is this and this. It changes kinetic energy final minus kinetic energy initial. So we can use work net is equal to final kinetic energy minus initial kinetic energy. So the change in kinetic energy is equal to the net work done. An example of that would be the nail and the hammer. Okay, and I'm going to read this, but I want you to look at the diagram as I'm reading it. A moving hammer strikes a nail and comes to rest. So as the hammer hits the nail, it comes to rest. It exerts a force on the nail. The nail exerts a force on the hammer. This is Newton's third law, equal in opposite directions, right? The work done on the nail by the hammer is positive. Okay, so with that again, the work done on the nail by the hammer is positive, so we got positive work going this way. The work done on the hammer by the nail is negative. So we can have negative work and positive work. Okay? We know that the change in kinetic energy is going to equal the change in work. So there's all kinds of work things that we can look at here. But just understand that this idea of Newton's third law and forces going back and forth and work being back and forth and almost opposite of each other comes to play a lot when we look at different situations. So here's a question. How much work is required for a 74 kilogram sprinter to accelerate from rest to a speed of 2.2 meters per second? So again, work or work net, right, is equal to change in kinetic energy, which is equal to kinetic energy final minus kinetic energy initial. So let's do kinetic energy final. It's 1/2 m, our mass of 74, times the v of 2.2 squared. Now our initial kinetic energy, since we're accelerating from rest, we know that that means our velocity is, 74 is 0, which makes that whole thing 0. So really, our net work in this case is just the same as our final kinetic energy. And when we punch those numbers in, 180 joules. That's how much work is done based on the change in kinetic energy. Another example. We got a student lifting a box from rest. It's going vertically with an upward force of 52.7 newtons. The distance is 1.6 meters. You can see the drawing over here on the right. Find the work done by the student, the work done by gravity, and see actually the final speed of the box. So let's look at part A first. Part A, we want to look at the work done by the student. Work, force times distance, okay? So we know the force being applied is 52.7, and the distance traveled is 1.6. So the student is doing work equal to 84.3 joules, okay? So that's student work. Part B is the work done by gravity. Now we have to do a little bit with this. To understand the work done by gravity, we have to take mass times g. So we take the mass of the box, 4.1, times 9.8, okay? And when we do this, we get approximately 40.2 newtons. So that's the force gravity's pulling down as this force is being pulled up. So the work done by gravity is going to equal the force of gravity, 40.2, over that same distance of 1.6. And we get negative 64.4 joules. Okay? So we know the work done by the student, we know the work done by gravity. Now we want to find the final speed of the box. That's where we use the work and kinetic energy theorem. Work total equal to kinetic energy final minus kinetic energy initial. Work total is going to be the work total is going to be 84.3, the work that student does, minus the work of gravity going downward. And when we do that math, we get 19.9 joules of work total, right? Since we start from rest, our initial kinetic energy is 0, but our final kinetic energy is 1/2. The mass of the box is 4.1 v squared. And so we're going to solve for v. All right, we're going to multiply by 1/2, divide by 4.1. Divide by 1/2, divide by 4.1, and then take the square root. But our velocity in this case equals 3.12 meters per second. So that's the velocity it has when we get to the end. So that's another use of this idea, or this theorem. And then here we have a boy pulling a sled along a pretty much frictionless surface, right? Does 19 joules of work as he pulls a 6.4 kilogram sled to a distance of 2 meters. No other work is done on the sled. If the initial speed of the sled is 0.5 meters per second, what is the final speed? Again, when we talk about work and speed together, always go to this idea of work total equals kinetic energy final minus kinetic energy initial. And our work final, our work total is 19. Kinetic energy final, 1/2. Our mass of 6.4 kilograms. And we're trying to find the final velocity. And we're going to subtract from that 1/2 times 6.4. And our initial velocity, we said, is 0.5. And we want to square that. Don't forget to square your velocities. And we're going to solve for v squared. Ideally, you would solve for this, add it over to the 19, so bring it over to here, and then you divide by 1/2 and 6.4, take the square root. The v turns out to be 2.5 meters per second. Before, when we did all this kinematic stuff, you can see that we can, with working kinetic energy, we can find speeds maybe easier, depending on your propensity to do the math. Lastly, kind of a thought problem. We want to take a car from rest, and we want to accelerate it to 2v. 2 times velocity, whatever v is. We want to, okay, and so it says, is the work required to accelerate the car from v to v2? So we want to find the work from here to here, okay? Equal to w, 2w, 3w, or 4w. Well, first off, we want to think about what happens when we double the velocity. We talked about this previously. If we double the velocity, okay, since we square it, right, it's going to be 4 times. So our work is going to be 4w. So we start at 0. To get to 2v, we go to 4w. But all the question's asking, we want to know the work to accelerate from v to 2v. So it's going to be less than 4w, obviously. And what we do is we just go, okay, well, if we want to go from, if it takes w, right, to go from 0 to v, and it takes 4w to get to 2v, the difference between those two would be the difference between these two, or 3w, 3 times the work is required.